Hello and welcome to our presentation on teaching numeracy and mathematics through computing science at BGE. This session will focus primarily on the primary school phase of BGE, but could easily be adapted to suit early years or secondary students as well. Why have we chosen to link numeracy and mathematics with computing science? Indeed, for our team, they go hand in hand. There's obviously lots of different curricular areas that maths links to, lots that computing science links to, but we feel that these two are very similar, and once we have a look at some of the E's and O's, hopefully that will become clear. So the three main parts we want to look at for this are data handling, encryption and binary, which might sound very unmathematical, but hopefully if you stick with us and watch through, you'll see the links that we've made here. A document I'd like to point you towards is the What Digital Learning Might Look Like document that we published earlier this year. It's available in Education Scotland Improvement Hubs. If you just simply Google what digital learning might look like, we've created a resource bank or an ideas bank of activities that could be used alongside the E's and O's for digital literacy and computing science from early through to second level at the time being, and hoping to add to those, and these activities are just a starter for 10, give you some inspiration on what you could be doing with your learners. So well worth having a look at that document. Again, back to the why. Digital skills, so important, as this Skills Development Scotland graphic points out, just how much digital technologies contribute to Scottish economy. That means jobs now and in the future for our young people. And if we break that down a wee bit further, you can see big data and artificial intelligence are the two most in-demand emergent technology skills. Again, coming from Skills Development Scotland, their summary report there. And again, data, absolutely huge. And when we start to think about how it's used in our lives, that's definitely an area to have a discussion with learners and to make them aware of how data is used in the world around us. But again, when we start to think about world of work, data is a huge part of that digital world. The approach we would always encourage people to take is a problem-solving approach, and what I've used here are the 4 creativity skills as defined by the Creative Scotland there. So we've got curiosity, to open-mindedness, to imagination, and ultimately, if we want to have real creative learning, we've got to have a problem-solving element that finishes this process off and hopefully sparks further curiosity. So indeed, computing science, computers in their very nature are designed to solve problems, and that's the way we'd like to see that being used in terms of learning and teaching, is that learners have got a problem to solve and they see computing as part of the solution to that. What I've taken here are the E's and O's for early first and second level. You can see here at early level, the red boxes are some of the things we're going to look at in this session. So again, to be able to classify and identify patterns. First level, we're looking at decisions based on logic. That would be the use of data to justify or inform a decision. Understanding how a computer works, and again, thinking about solutions and improvements. So hopefully, again, looking at data and seeing how that could provide a better result. Again, structuring information, how it's used in the real world, the roles of different parts of the computers, how they all work, and indeed binary is quite explicit there under that understanding and analysing, organiser at 214, and again at number 215, really thinking about coding there and computer programming, but again identifying patterns and solving problems that could easily be databases as well. So in terms of data handling, if we start there, having a think about who uses data, what they use data for, and why are these companies, not only these companies, but these companies are very well known for their use of data and the amount of data that they handle. Is it relevant for Scotland? And again, if we're thinking, why should we teach about how Amazon works? If you consider how Amazon, Netflix, Google and Facebook, huge multinational companies, employ lots of people, but I would even suggest that wanting the best for our young people, our learners, it's not about getting them to aspire to work for these sort of companies. What we'd love is, obviously, for young Scottish people to be the next Amazon, Netflix, Google or Facebook, the next innovator in digital technology. So that's what we should really be aspiring for with our learners. Again, just a reminder there of how big data is in Scotland. Definitely part of the reason we should be teaching that. Again, just before we get on to the computing science element of it, the numeracy and maths model here, what I really like is that it's not got arrows showing a flow from concept to conclusions, but rather that it's a process that can be backwards, forwards and sideways. And again, that's analogous with the way that our learners learn indeed. So again, that could easily be a basis for understanding data and data science. So a real good model, well worth having a look at that for planning your numeracy and maths and then leading into your computing science. There are obviously E's and O's that match up to early level, but for the purposes of this presentation, I've just gone through first and second here with you. You can see there's a wee link to Bite Size from BBC explaining what a database is up at the top, and that's the part we're going to focus in here. I think in early level we'd probably be talking about data and indeed sorting and categories and characteristics. Indeed, Boolean logic comes in at the early level. Skills for mathematics, where the learners should be able to state whether something is or is not, such as, the car is red or it is not red. And that Boolean logic comes in further on in computing science with coding and programming as well. So really essential skills at the early level, but in terms of data and databases, it's likely something you're going to actually apply with older learners here. So again, talking about using digital technology to find and to present information, different ways of doing that, and you can see in the maths E's and O's on the right hand side, there's quite a lot of similarities between organising and presenting charts, tables. You see the same language being used there. At second level, again, using technologies to search, access and retrieve information. I think that's very often considered to be the use of web search engines, but in fact that a database is somewhere you would also access, retrieve and search information. And even that part at 213 about structuring related items, and again a database is most powerful when it is relational and it links things together. And you can see there that it's carrying out surveys and investigations, for example, and then organising those in an appropriate way. And I think this one's really important at 220 in the top right, about recognising that the presentation may be misleading. So just because a graph makes it look like the 10-year-olds in a primary 6 class have all named pizza as their favourite food, is there a correlation between being 10 and liking pizza? Probably not, but learners should obviously have experience of false conclusions like that, or misconceptions, and having that discussion about why it is or is not a true representation. So again, huge in the field of data to have that discussion, that emotional intelligence around it. So what are we going to do practically then? Well, what I would do is having a think about databases is the place to start. Databases can be dependent on your local authority or your school's access. You might have use of Microsoft Access, but it is dependent on having that set up and having a server. I've used Airtable for my examples. It's free to sign up. It's online. But again, you'd obviously have to speak to your ICT coordinator, your low-key contact, or internet safety officer about using any kind of web-based software with logins or sign-ups for your learners. Check that out. Keep yourself right in terms of GDPR. But where to start? Well, what we want to do in terms of learning and teaching here, we want to know something, we want to be able to prove something, and we need the data to be able to do that. So again, it's about learners being able to identify what their need is, what this problem is that they need to solve, and the data that they require to be able to solve that. In terms of the knowledge of data science there, they've got to understand what a record and a field is. If you're familiar with spreadsheets, you're probably thinking of rows and columns here. In terms of a database, this is a record, and this is about student 6, who is Sari Eisenhower. She's female, she's 10, and she's in the blue maths group, but this is the record. All of this information relates to student 6, and the fields such as name, gender, age, these are the characteristics we can hold in that record. And how we're going to collect that data, I would say that's certainly up to you and your learners. They'll have many imaginative ways, whether it's a survey, an online poll, or making use of forms or quiz software to collect data from people in a wider sphere than perhaps their neighbouring classrooms. I've created a couple of example databases I'd like to use just to demonstrate quickly the purpose of a database and how we can use that for the computing and the mathematical learning. So here is my database for my primary 6 class, and you can see I've got a table here. I've got some others, but I'm not going to utilise those at the moment, but I've got a table of pupils. And again, so I've got the ID here, which is unique to every record on the table, which is important for understanding in databases. So every single record has a unique number. I could have 2 Latia Blaszeks in my class. They could both be female and 10. How would I know which one was the one I needed to know about? How could I differentiate them? In a database, they would all have a unique ID. And you can see, even if I change the order, if I sort here, if I sort them in descending, you'll see here, although the rows still are numbered 1 to 20, the ID changes, and that sticks with the learner regardless of how they are sorted. What a database lets me do, you might be thinking, why would I use a database and not a spreadsheet? I'd always use the example, you could cycle to France, but you'd probably find it easier to get a train or a plane to France, because those are perhaps more suitable for that journey. A database is more suitable than a spreadsheet for storing data and to be able to sort, order and analyse that. Spreadsheets are great for creating graphs and charts, but when we want to present data or store it or handle it, manipulate it, databases are indeed the tool to use. So I've got the fields here, so I've got the names of the learners, their gender, their age, their maths group, the literacy group, favourite food, pets and sport. And some of the tools I can use here are, I can filter it. So if I only want to look at learners who are perhaps 10, and so I can filter that down to only show me the learners who are 10 years old in the class, so that's half the class, and I could then group them by their maths group perhaps. So group them by maths group. And it'll now show me, so these are only the 10-year-olds, and you can see most of my 10-year-olds are in the squares and the triangles, and I've got a couple in the circles here. So again, I can split it up, and unlike when I'm filtering, they're split up by their groups, but I've still got everybody available, and I could then sort them within that as well. A couple of sorts already there. If I take this one off, this grouping, let's remove the filter as well. So I've got all my learners in my class back again, and if I grouped them by their maths group, and then asked it to sort within those groups by their favourite food, so that's a wee bit easier to look at. And I can have a look down here and I can see in the circles, we've got lots of fish and chips there, etc. So I can have different groupings, different sortings, and I can also have multiple sorts at the same time. So I could then ask it, after they've sorted by food, to then sort within food by their gender. So once it's picked for heaters, it's going to be male, male, steak pie, male, male, and depending on here for haggis and totties, for example, I've got female, male, so it's going to sort by gender after it's sorted by favourite food. So there's lots of different sorts, groupings and filters that I can apply on that. And it could be, you might want to ask your learners if there is a correlation between if they're grouped in the circles and if there are more boys than girls in a group, or if there is a preference for food. Does this relate to the group that they're in? And the obvious answer would be no, but they might want to be able to draw conclusions from that. Again, with a database, I can add as many fields as I like, and what that's doing is that's building up a picture each time. If I pick here on person number 3, you'll see this is Amy Flaws, she's 9, this is the maths group she's in, it's the literacy group she's in, her favourite food is pizza, it tells me who else likes pizza, she has a pet dog, her favourite sport is hockey, and that's unique to a database where each record, all of that information in the different fields is related to that person. It's related to person number 3, which is Amy, and it's shown me where she relates to other people, how many other people are like her. And if you then imagine that in the context of a shopping website, for example, and it's got each record as a customer, and it knows your age, your name, your gender, your location, the things that you've bought and who else buys things like that. Do you know people who have bought the similar thing? Is it telling them that your friend has purchased this, perhaps you want to purchase it as well? And again, going into different groups. So it's incredibly powerful to think this is just an example student that I've made up, but I've got quite a lot of data on that person, and I could then use that to perhaps market things at her. And again, I think that's where part of your learning would go. Certainly in the upper parts of the BGE, would definitely be looking at that, influencing the ability to influence people based on the data that you have. So that's quite a simple overview of databases. We've got records, which are in the rows, and that is about each person, each unique ID, and then we've got the fields, which are the categories we can use to sort, order and draw conclusions from. Of using shapes, and again, anytime we need to display information about objects, so this time the square has 4 sides, 4 corners, 4 axes of symmetry, and there's an image to represent it. If I choose to expand that, it shows me all this information about a square. So that might even be useful for learners when they're learning new ideas to build up an easy table like this. Quite a simple flat table where they can add different characteristics. And again, it's quite easy to spot patterns. If I look at sides, shapes which have 4 sides, we could look at the similarities between them. They all have 4 corners because they have 4 sides. However, they don't all have the same number of axes of symmetry, and you can look at the images there to understand why that is. So again, really useful to be able to sort, order and filter and help learners. It might be that you create databases or tables like this, that your learners just use them as a knowledge base to find out facts, or it could be your learners are going to create those. Again, I think before we get to databases, we want to make sure that our learners are secure in their knowledge of sort of concrete and pictorial representations of data. So that could be sorting and ordering cubes or toys, balls in the PE cupboard. Do all of the balls go in the same place in the PE cupboard, or do the hockey balls go beside the hockey sticks and the footballs go in a separate basket or cage? Or do we want all of the hockey equipment together, or do we want all the balls together? So different ways of sorting and order real life things. And then also at a pictorial stage, you maybe want to have covered Venn and Carroll diagrams or branching diagrams that let us make decisions to sort and order information. So there's lots of steps to go to, but I'd say tables and databases are definitely an area to look at for progressing the learning. That leads us on to the next part. This graphic has come from Barefoot Computing. Again, if you're going to have an internet search for Barefoot, I'd suggest you put in Barefoot CAS, C-A-S, or Barefoot Computing. It allows you to get lots of pictures of people's feet on Google. But if you sign up to Barefoot, it's free, tons of resources there, and they're all geared towards CFE as well. So that's great to have Scottish specific learning resources. This idea of the computational thinkers is quite often used to think about programming and coding and the steps there, but indeed they work in all parts of computing science, especially data here, where you're predicting or analysing information, you're making judgments based on the data you have and the patterns you can identify, making steps and rules, and that's again about talking with your learners about the records that you're going to create in a table. What are the fields, what are the characteristics that are going to distinguish to help you sort and order that information, and that is your steps and rules there. Once you've got your table, can you spot any patterns or familiarities or similarities, and breaking things down into their parts? So what are the most important things I need to consider when I create my fields? If I'm going to collect information about mammals, perhaps for classification in a science lesson, I want to create a table of mammals. Perhaps the number of legs is not distinguishing enough. You'll find that a lot of mammals have 4 legs, there's some with 2, or classifying mammals that have hair is not going to really give you much to go by. So you perhaps have to consider there what are the differences between different mammals. Is it their biome, their diet, are these things that are going to give you clearer sorts and filters in your table. And again, that last part, similar abstraction about removing unnecessary detail. So again, you probably don't need in a table of fish to classify which fish swim and which fish don't. It's probably not a necessary detail. Does it swim when you have a table of fish? So again, those are computational thinking concepts and applicable right through data analysis and numeracy and maths as well. And understanding that computational thinking and how a computer works leads us to this next part, where I think cybersecurity, it's all about patterns and sequences. You can see there, and again, to have that persistence and resilience to see a problem through to its end. So what I've put on the screen here is a simple pig pen cipher, and over on the left hand side, these 4 sets of letters are the key, and this is the message. To be able to read the message, you've got to decrypt it using the key. So it's spotting patterns, and you'll hopefully identify here that this shape relates to this shape around the C. This triangle with the dot relates to the Y. This U looking shape relates to the shape around the B. And once you start to crack that pattern, you'll go through the rest, and you can probably even make a prediction about what the message that I've written on the screen indeed says when it has been decrypted. And you might look at it and say, well, there's no numbers, where's the numeracy, where's the mathematics? But firstly, that I'd spotting patterns and working through in a logical order, and indeed the resilience to keep going with a problem are all mathematical skills. But in terms of cybersecurity, true, it's not going to have letters and symbols likely in the encryption, but everything that you do online should be encrypted. If you think about social media apps, your banking, websites, when you visit a website, and we're telling learners to try and stay safe online, only using websites that have HTTPS and the wee padlock up in the URL bar at the top of the browser. That is all to do with encryption. How is encryption done? It's done using large complex numbers, which are checked to be secure using large prime numbers and complex calculations. So it's all mathematical work that is being done by the computer, which is indeed a mathematical machine itself. So for your bank details to be safe, your message gets sent to the bank, but it is encrypted, and it will look like this. It will look like this on the screen, unless the other end, your bank has the key to unlock it, and that would stop someone from stealing it. So if someone tried to intercept and steal your communications with your bank, they would get something gibberish like this numerically, but they would require a key to unlock it. So again, it's that principle of encryption and decryption and how that is done. And as I say, probably further on in your numeracy and maths, but it's large numbers, prime numbers are important there too. And again, you'd have to be able to work in some incredible patterns to crack a 250 digit encrypted number. So that is where indeed cybersecurity is very mathematical. And when we want to think about the story of cybersecurity and indeed decryption of messages, there's no better example than Alan Turing, perhaps, and the team that he worked with at Bletchley Park during World War II. And I hope at this point there's lots of people saying, but I teach that. I teach code breaking as part of World War II, and that's fantastic. And it's perhaps just about considering at the design stage of your learning that we're bundling that the E's and O's around computing science in there, because spotting patterns is a part of computing science, and it goes right alongside that numeracy and mathematics. So if you're teaching World War II, absolutely stick to talking about Alan Turing, Bletchley Park, and the Enigma machine. But also thinking about how that was computing science, and the work that Alan Turing indeed went on to do after the war was hugely important in the field of computing. So that's perhaps even a whole other aspect of your World War II learning to look at is the story behind Alan Turing. And you can see here there's a wee link to the Barefoot resource on code cracking, which again relates to World War II and all the work done there. And it gives you some simple examples such as a substitution cipher where A equals 1, B equals 2. But again, what starts to happen, you can make those more mathematical, where you move every number, multiply it by 4, and then add on 2 to make it more complex. So you're using mathematical rules. So there's lots of examples there in the whole topic of learning in that Barefoot resource site. And again, Alan Turing, a great example to take forward as someone who was important to computing, and the work that he did was indeed around encryption and decryption, which then leads on to this. These E's and O's about understanding the impact of maths on the world and famous mathematicians. And you're perhaps thinking, I don't know many great mathematicians, but when you consider that, as I said, the computer is a mathematical machine, here's some examples you might want to consider. So I mentioned earlier Boolean logic, which was created by George Boole, and based on a binary number system, which I think the oldest example was I Ching, which was a Chinese number system, many thousands of years ago. So mathematics, these people were all mathematicians who contributed to computer coding and programming. These people have been instrumental in the design of computer systems. Again, the web and the internet, there are people in groups here to look at. And if you want to take it to something perhaps really relevant to your learners, you want to consider games. And we've got some David Jones from Scottish company DMA, and Chris van der Kuil there from 4J, who were responsible for Minecraft. So again, you want to spark your learners' imagination, let's talk about Minecraft and how it is linked to maths. So I think to do a whole topic of research around famous mathematicians, and we learn so much of our knowledge and understanding through stories. So if you want to make those concepts in computing or maths more relevant to learners, think about the story of the people behind them. I mentioned there George Boole's Boolean logic, which was based on Charles Babbage's work as well, which ultimately is that binary counting system, and that's how every computer works. So there's an old joke that there are 1-0 kinds of people in the world: those who understand binary and those who don't. So binary is a number system which only uses 2 digits. It uses 1 and 0. So it's a base 2 number system. It only has two digits to use there. Again, I've put some links to BBC Bite Size. I've got a presentation here on PowerPoint I'll skip to in a wee second. And again, Barefoot resources. Again, if you follow that link, there are ideas there on binary work as well. So I'm going to open up this other slide. And I'm just going to go through it in this view here. So it's perhaps worth discussing with learners our number system, what their understanding of that is, what happens when you have more than 9 in the units column, what happens if we add 1 to that. Again, simple graphical demonstration here that you can only have 9 in the units, and when you go 1 more, we've got to move to the left into a new column which is called the tens. So the most we can have, we can put 10 different digits into each column, 0 through 9. But when we have more than 9, we have to move on, and that is our decimal number system. So you've got to have a bit of a good grasp of place value and how that works with decimal. Binary, the computer can only understand 0 and 1 because it works in electricity, and electricity is either on or off. You can have different amounts of electricity, but it's still either it is on or it is off. And a good way of demonstrating that is perhaps with a tap in the classroom. It's on, it's off, or even with the light switch in the wall, it is on or it is off. And that is how a computer works. That's the only logic it understands. The information is true or false, yes or no, 0 or 1. Yet they can do so many complex things, and it's built in this number system. So in here I've got the number 1, and it goes in the first column, so I can represent 1 here. But if I'm going to have a bigger number than 1 to represent 2, well, once this column is full, it can only have 0 or 1 in it. So to represent the number 2, I need to go to the next column. So I now have a 1 in this column, and I have a 0 in this column. So if this is the ones column, and this is now representing the number 2, I have one of these, have a guess, this is the number 2 column. Again, I can now represent with a 1 and a 1, and so I've got a 2 and a 1 here, that number here, 1, 1 is 3, and to get to the number 4, again, I can't have more than 1 in a column, I've got to move across to the next column, and that is in my 4s column here. So again, pattern recognition, 1, 2, 4. You can have a guess, is the next column going to be the 6s or the 8s? I'm sure you're going to use your problem solving skills here, your logical thinking, and realising that I can indeed show 4 by with a 1. I can show 5 by having 1, 0 and another 1. I can move to 6 with a 4 and a 2, and I can have a 7 with a 4, a 2 and a 1. So the next column will be the 8s. So again, an understanding of base 10, your decimal and place value is important, and there it is there. So you see the 1, 2 and the 4 columns, and that goes on. It doubles each time. So again, about identifying patterns, and you can have a go with some examples like this. So how would I represent the number 10 here? And I'm sure your learners could even tell you that you would need an 8 and a 2. So you put a 1 in the 8 column, a 1 in the 2 column, and then to hold place, we're going to put zeros in here as well. So number 10 would in fact be 1, 0, 1, 0 in binary. A wee quirk to remember, and to definitely go back to your learners, the number, if you're using 4 bits for place values to represent numbers, then you'd have to hold the place value in front of your first one as well. So it would be 0, 0, 1, 0 if you were using 4 place values, 4 bits of information to represent that number. Complex, it depends on your knowledge of place value and how familiar you are with that. I'm sure the first time you're hearing it, you might think that's quite a complex number system, but in fact it's only got 2 digits. You could argue that it's even simpler than decimal. It's just that you've never tried to count with it before. So hopefully this joke makes a wee bit more sense. There's a 1 here, there's a 2 here, so 2 kinds of people in the world, those who understand binary and those who don't, but 1, 0 is the binary representation of the number 2. So again, core programming language, you want to understand how a computer works. It uses binary to its core, and again, understanding how computers networks, it's all based in binary, and I've tried to link these maths knows here about pattern recognition. We've got here different number systems that were used. So as I mentioned, the Chinese used binary thousands of years ago. I think there were South American civilizations that used hexadecimal, so used a base 8 counting system. So you got to 8 in a column, and then you had to move to the next column to make a 9. So different examples all over the world. I think even if you consider in French that the number 80 is 80, which is 4 20s. So they're counting in a dual decimal system for those large numbers where you have 4 groups of 20. That's how they literally explain the number 80. So again, thinking about large numbers, place value, patterns, and again, continuing a sequence. So to get to larger binary numbers, I wouldn't expect learners probably to go much further than 20 in binary at primary school, but I think once your learners have a grasp of place value and they're talking about hundreds of thousands, tens of millions, yes, you can continue to billions and trillions, but by then I think your learners are probably secure enough in how large numbers work, and you can make large numbers, but once they know that rule, they're probably very confident at using large numbers. So here's a great way to challenge them with a different number system that uses different place value, and that would be great to really to be able to check if a learner truly understood place value. If they can use those rules in a different number system, then that would certainly prove that they were confident in place value. So yeah, just a wee recap of some of those slides here. I've put links to CS Unplugged in the presentation as well. You follow that link in the PowerPoint that I've attached to the video, and it's got these great pictorial representations of binary problems. So, learners, what do you think the next number is going to be? Is it going to be 6? Is it going to be 8? Is it going to be something totally different? So they've got these pictures they can work through it, and this one at the bottom, whose cake is it? Is it the 10-year-olds or is it the 2-year-olds? It depends if it's a decimal or a binary number. So lots of different ways we can teach binary, and I think it's just that fun way of exploring maths and numeracy with a different type of number system that perhaps your learners weren't aware of. So again, just to recap that, throughout all of these, whether it's databases, encryption and decryption, famous mathematicians and computing scientists, or binary, it's thinking about what is the problem that we need to solve, and it's the way that we probably teach so much of our numeracy and maths already, and that's the model I would like to propose continuing with. The way that you would normally teach your maths with a problem and thinking about how your learners are going to solve that problem, how you're going to support them and challenge them or scaffold their thinking to get to that position where they can solve a problem, and then how you're going to assess that, all the same stuff, and we can just bundle computing science in amongst this. It's probably the same way that I would teach computing science that I would teach maths as well. So hopefully nothing new in terms of the methodology there, just different ideas of how you would do that. So thanks very much for joining us. I hope that's been useful. As I say, I hope more people watching felt that there was certainly a lot of familiarity with things that they were already doing, and sometimes it's good to just see that others are on the same track as you. Perhaps there's some people who have sparked some new ideas or made links that they didn't realise that they were already doing it, but they didn't perhaps join the dots there. So hopefully that's come in handy, but do let us know. Get in touch with us on Twitter at DidYouLearnScott if you watched that, you found that useful, or you'd like to see more in that series. So thanks for joining us, thanks for watching, and stay safe and enjoy teaching computing science and numeracy and mathematics together at the BGE.